So next problem. So example number 9. Okay, so we have two runners running, say, a 100-meter race. I don't know if the numbers in this problem end up being realistic, but let's just say they end up being realistic. So two runners run a 100-meter race, right? So we just have a single track, right? Here's the starting line, here's the finish. The whole thing is 100 meters. Now, I have two runners, but actually one of them is going to get a head start. So the first runner, starting point, that's my finish point. So the first runner will actually start at the starting line. So runner A actually does start at the at x equals 0, right? He starts at the finish line, or start the starting line. Runner B, though, rather, gets a little bit of a head start. So he starts at, let's say, this is x equals 8. So he starts about 8 meters ahead of the other guy. All right, now I know the velocity of each. The velocity of the runners, the velocities of the runners are, so the velocity of runner A is 2t, and the velocity of runner B is just 2. So in other words, the runner B actually has a constant speed. So that person just runs at a constant speed, and velocity A, runner A actually starts out at a very small speed, right? If t equals 0, he's basically not even running at all. But as t increases, we can see the velocity increases. So runner A kind of gets faster and faster as the race goes. All right, so what is the question? The question is, does A ever overtake B? Even though B got a head start, does A actually end up getting ahead of B? And then the second question is, so let's say that that's part A. And part B will be, how long does each take to finish the race? So again, I'll make that very clear here that the finish line is at x equals 100, right? So both of them have the same finish line, just runner B has a 8-meter head start. Solution. Now, if you're not sure how to do this problem, I'm going to tell you that it's from 5.1, antiderivatives and initial value problems. So I'm going to give you a few minutes to work on this, but first I just want to talk about how you would go about solving it just very quickly. How would you determine whether A overtakes B? I mean, you have to think about what that means. Does the position of runner A ever equal position B? And then you would like to know that the position of A is then thereafter that time kind of greater than, right? I mean, in other words, you at least have to know what is the position of each runner, right? To understand how much, whether one runner overtakes the other. And also, how long does it take each runner to reach the finish line? If you knew the position of each runner as a function of time, you can just set their position equal to 100. Say, for instance, if I knew the x position of runner A, I'm going to set that equal to 100 and then solve for t. So for either part, what do you need? You need to find out the position of each runner, right? So I'm going to write that as a preamble. We need the position of each runner. as a function of time. So think about how you would answer that, right? How would you get the position function for runner A? What information are you given for runner A? How would you get the position function for runner B? What information are you given about runner B? Okay. I'm going to give you, we have only about 14 minutes left of class. So unfortunately, I'm just going to give you 5 minutes to work on this. At least try to answer this first question. At least try to get the position of runner A and runner B.
Quick question.
Yeah.
So when we like solve for the position, I mean like when we're trying to solve for a position or whatever, do we have to find the constant C?
Yes, that's right. When you find the this is an initial value problem, right? You use an antiderivative, and you're going to need that plus C for each of them. And you get that plus C using some other piece of information. But yes, this is one of those plus C type problems.
All right, thank you.
Welcome.
Oh wait, another question.
Sure.
My bad. So can there's like can the constants be different for the two things?
Yes, of course they have to be. You have to allow the constants to be different. Yes.
All right, thanks so much.
Don't worry if the numbers turn out to be unrealistic. Recording for both lectures will be available. The recording for the first lecture is probably already available. It will be in them. They will also be on YouTube, and the notes will be available, and so on and so forth. Angelica?
My computer died. I just logged back in.
Alrighty. So, in the interest of time, I'll kind of just skip the polls and we'll just go right into solving this problem. So let's first find the position of each runner. Okay. So what do we know for each runner? Okay.
Runner B has a head start.
So how can we actually describe this mathematically? So I am looking for the position of XA. So I know, for instance, that XA prime of t is equal to 2t for runner A, right? If I want the position XA, I'm given its velocity. That's actually I'm being given the derivative. The same thing for runner B. I'm given the derivative of runner B's velocity. Oh, sorry, the derivative of runner B's position, and that's equal to 2. Since that says XA of 0 is equal to 0, right? He does not get a head start, but runner B does get a head start. XB of 0 is equal to, what was it? 8. Okay, so now let's solve this. So we have two initial value problems to solve. Okay, so let's again keep this kind of in columns. So the position I can get by taking the antiderivative of 2t. And what do I get? I get t squared plus some constant, which I'll call CA, right? Because the constant is not the same for both of these runners. And now for part B, or for runner B, I can say that his velocity is, again, the antiderivative of his position is the antiderivative of his velocity. So I get here 2t plus some constant, and that might be a different constant. Let me just put a vertical line here, just so it's easy to separate them. Now I'm going to use the initial value, right? XA of 0 equals 0. So 0 plus CA equals 0. So CA equals 0. Right, that's kind of one part of the problem. That's the next part of the problem. And then I can conclude that the position of runner A is simply t squared. What can I do for runner B? Okay, his initial value was 8. So I get 0 plus CB equals 8. So CB has to equal 8. And so now I can conclude that runner B's position is 2t plus 8. Any questions about either of these two positions? Are there any questions about getting the position of either runner? How did you do the second part to find C? So all we did was, so for instance, if I look at part B, oops, the given information was that at t equals 0, runner B starts at 8. So what I do is I plug in t equals 0. I plug in t equals 0 into my function, and I get 0 plus CB. But I'm told that it's supposed to be equal to 8. So in other words, I just get immediately CB equals 8. Right, notice you're doing two things here, right? When you look at this initial value, XB of 0 equals 8, you calculate XB of 0 using the function you already have with the constant. But then you set whatever that is equal to 8 and solve for the constant. Okay. Any other questions about getting those two positions? I'll make this a little bit neater in the notes. Why did you out 0? Put 0? Well, we were told that the runners start at different times, right? We're saying the starting point is t equals 0, right? So at t equals 0, the first runner is at x equals 0, and at t equals 0, the second runner is at x equals 8, right? They start at different times. T equals 0 is the start of the race. All right, now let's answer each question. All right, so the first question was, does runner A ever overtake runner B? how can I actually determine that? So let's actually graph these two things. So runner B, his position is 2t plus 8, right? So that just looks like a line. In fact, let's not put anything to the left because it actually just starts at t equals 0. So it's just kind of this ray, right? So this is xb of t. Now, what about the other runner? So he starts at the starting line, but then his position is x of t equals t squared. And we know that because this is a square and not just a power of 1, because this is a higher power, eventually this actually will overtake the lower power. So it's a matter of just finding out where does he actually overtake. Right? Why is that the time at which A overtakes B? Because notice to the left of this time, so let's call this t equals, say, c. To the left of t equals c, runner A is at a smaller position than runner A, right? Remember, this axis, this is the t-axis, and this is the x-axis. So if you want to compare the positions, like let's say this is t equals 1, the position of runner A is over here, and the position of runner B is over here. So B is still ahead of A. But then once you pass that intersection point, now A will be ahead of runner B. So like let's say this is like t equals 6. Runner B is over here, and runner A is all the way up here. Okay. So let's see. When does so the answer is yes. A does overtake B. Let's find that out. So A overtakes B, obviously, when their positions are equal. So I get t equals 4 or t equals -2, but obviously the t equals -2 is out. We don't have negative time. So runner A overtakes runner B at t equals 4. So 4 seconds into the race, A has overtaken part B, and runner B's head start is immaterial. Now, in the last minute of class, let's just solve part B. Part B asked, how long does each runner take to finish the race, actually reach the finish line? Again, let's look at runner A and runner B. So if I want to know when they actually cross the finish line, all I need to do is set their position equal to 100. T is positive, so oops. So runner A reaches the finish line after 10 seconds. Runner B gets to the finish line at 46 seconds. So quite a long ways ahead.